Hey, folks. Welcome aboard. We have been talking about the finite field in which AES does its computations. I want to go over the algorithm itself, the sort of the overview of how AES works. AES uses a 128-bit block size. That means if its message that it's encoding is longer than 128 bits, it will divide the message into units of 128 bits and process each of those units separately. Um, there are three levels of security depending on how much key you want to store and how much time you want to take to do the encryption. You can use a 128-bit key with 10 rounds, which reduces your storage requirements and your time requirements because it takes fewer rounds. And then it scales up to a more secure mode. We could scale up beyond 256 bits and 14 rounds as well, but the specification includes these three levels of security. So these are the ones that we'll be implementing. All right, so here's the initial part of the process. This is the algorithm itself, but this part, what's called key expansion, and we'll talk about this at the end of the video today. It takes this initial key, whatever key this is, and generates enough data from this key so that we have a key for every single round. So instead of having to generate 10 128-bit keys, we're only generating one, and then the expansion routine is taking that data and generating enough keys for all of the different rounds. That's how this works. So there will be one key for every round plus an extra key. The last round will always have the key being two keys being used instead of just one. So we start with the plain text. We go through 4 encryption steps in each round. 1, 2, 3, 4. They're called add round keys, subbytes, shift rows, and mix columns. And briefly, I'll talk about each of these steps. And we loop through this for however many rounds that we have, except for the last round. So if we're using the 10 round mode, we would go through this loop 9 times. And then the 10th time, we would go through this step, which replaces the mix column step at the end with a different add ground key step. This replacement here, we talked about this about a week ago. It makes the decryption process less computationally intensive, and we are not losing security by replacing mixed columns with an add round key. So the very last round is just a little bit different. It's also the reason why we need 11 keys for 10 rounds, and 13 keys for 12 rounds, and 15 keys for 14 rounds, and so on and so forth. We always need one more key than the number of rounds. All right, so we're going to look at this part first, and then we're going to get to the key expansion part at the end and look at it in a little bit more detail. So the add round key step is just an XOR step. We have a block of 128 bits here, and we XOR it with a 128-bit key. Whatever key that comes out of the expansion routine for that round. So the key scheduler produces a different key for each round, plus one extra key to use in the last round. So the first step is just an XOR. We have called the key scheduler. It gives us the first key to use. We take that key and we XOR it with the text that we have. The next step is sub-bytes. It replaces every 8-bit byte of the 128-bit block with a different 8 bits. So what's happening in the sub-byte step is that we have 128 bits, which are 16 8-bit bytes. Ten, 11, 12, 13, 14, 15, 16. Each of these 8-bit chunks of the 128-bit block goes through an S box. And we've talked about this before. It's just a lookup table. It takes whatever these 8 bytes are and gives us 8 bits, and gives us a different 8 bits to come out of it. And we do that 16 times here. There are 2 to the 8th values in the table. There are 256 rows in the table of inputs and outputs. That table's way too long to fit on this slide at a legible font size. But you can find it in the book on page 112. You can also find it in the AES specifications. So this is just a substitution step. We take each of these 8-bit chunks out of the 128-bit block, substitute a different sequence of bits for it. Okay? So we've done an XOR step. We've done a sub-byte step. The sub-bytes provides confusion because we are changing the bit patterns and the number of zeros and the number of ones and the arrangement of the zeros and ones can change on the way out of the S boxes. And then we're doing 2 steps that create diffusion, which moves errors and data, or not errors, but moves changes in the data around to different locations. In the shift row step, we take that 128-bit block, and that's 16 8-bit bytes. We're going to replace that, represent it as a 4x4 grid. So these are the first 8 bytes. I keep saying bytes, bits. First 8 bits, the next 8 bits, the next 8 bits, the next 8 bits, the next 8 bits, so on and so forth, all the way down to the bottom. We have loaded this matrix up with bits of data. And what we're going to do is we're going to leave the top row alone, but we're going to take the second row and rotate it one place to the left. So S11 goes here, S12 goes here, S13 goes here, and S10 goes around to the end. Then we're going to take the third row and shift it 2 places to the left. So S22, S23, and then S20 wraps around and S21 wraps around. And then you can guess what's going to happen to the third row. It's going to shift 3 places to the left. So S33 leaps all the way to the front, and then S30 goes after that, then S31, and then finally S32. So everything has shifted 3 places to the left, which is the same as 1 place to the right. So rotate by 0 in the top row, rotate by 1 in the second row, rotate by 2, rotate by 3. So the locations of the data are moved around. And then we do a matrix multiplication operation. Every entry in this matrix that we're going to use is either a 1 or a 2 or a 3. Or in our polynomial language, a 1, an x, or an x plus 1. Multiplying by 1 is easy, no change. And multiplying by 1, 0, which is multiplying by x, is what our x time function does. And multiplying by 3 is just like taking multiplying by 2, multiplying by 1, and adding those together. And so this can be done very quickly using the x time operation. So I've got an example on the next slide here. in the mixed columns step, whatever data we got after the shift rows, we now think of each of these rows now as, well, we work on each column at a time. There are 8 bits in each entry in this column, 8 bits in each entry in this column, and so on and so forth. And so we're going to multiply this matrix by these 8 bits. So we're going to get 1, 0 times this entry, which is just this entry shifted left, which means it gains an extra 0 on the right. And then 1, 1 times this entry, which is left shift the entry and multiply the entry by 1, which is just use the entry by itself. And then 1 and 1, which is just this entry by itself, and then this entry by itself. And then we XOR all of this together, and this is what we get when we're done. Okay? Then we do the same thing with the next row. So it's going to be 1 times this value plus 1, 0 times this value, so that shifts it to the left, 1. 1, 1 times this value causes this value to shift to the left and be included as is, and 0, 1 means we just include this value here. We XOR it all together, and we get an answer that's too long to fit in a byte. We get 1, 1, 1, 0, 1, 0, 1, 0, 1. And now if our answer overflows a byte, we XOR it with our AES polynomial, which is 1, 0, 0, 0, 1, 1, 0, 1, 1. And we get 1, 1, 0, 0, 1, 1, 1, 0. All right, and that's what we get right there. Then we do the third row, and this is the answer we get, the fourth row, and then we have an answer that overflows again, so we'll have to reduce like we did here. I'm not going to go through these other 2 calculations again. Okay? All right, so just reviewing what happens in a round. We have an XOR step here, then a substitution table where we take every 8 bits of the message and substitute them with a different set of 8 bits. Then this shift rows operation where we put these bytes into a 4x4 matrix. We shift the second row by 1, the third row by 2, and the fourth row by 3. And then we multiply the column that we end up getting by this matrix here that contains 1s, 2s, and 3s in it. And that can be done easily using X time. And finally, we've got, the text at the end of a round that now gets passed on to the next round and out. So none of those individual operations, I think, should be terribly hard to implement. So then the last thing we have to talk about is this key expansion business here. So we have to produce enough data with the routine to cover this number of rounds plus 1. All right. So the key expansion routine has an intermediate step that's called the key expansion core. The core step takes a 4-byte string, so it's a 4-byte string, so that's 32 bits. I don't know where I write this. So example, something like 3, 7, that's a byte, and then 2B, that's a byte, and then 51FC. There we go. So that's just an example of what we might do. What does it do? It rotates these bytes to the left. So we get 2B, then F1, then FC, and then 37. So that's what the rotate left step does. Then the S box is a lookup table. We look up each of these values and then see what they convert to in the table. And then we XOR with a constant. So this is whatever comes out of the substitution box. The constants are around 0. It's the polynomial representing x to the 0, which is 1. Well, that's easy. That's just that polynomial there. And then for round 1, it's the polynomial representing x to the first. Well, that's easy also. That should be a 1. And then so on and so forth. This works great up to round 7. So when we get to round 7, we don't need 2 7s here. We get x to the 7th, which is as big as we can fit in a byte. But we're not done yet because we have to have enough for every round plus 1, which means we have to go up to x to the 10th here. So let's talk about what happens at round 8. X to the 8th is too big to fit in a byte. And so what we do is we use the AES polynomial, which is 1 3 zeros and then 1 1 0 1 1, and we use that to cancel out that leading 1, and so we end up getting this answer here. And that's going to be the constant that gets used for round 8, and then so on and so forth. Round 9 would be x to the 9th, which is just x times this. Round 10 would be x to the 10th, which would be x times x to the 9th, which is x times x to the 8th, and so on and so forth. So just summarizing this again, rotate left takes each of these bytes and shifts it to the left. 3E goes into this position, 36 goes into this position, FE goes into this position. The S box takes every value and looks it up in a 256 row table and returns the value that comes out. So 3E becomes B2, 36 becomes 05, FE becomes BB, 0C becomes FE. All right. Then the round constant step multiplies, well, not multiplies, XORs so let me back up. The XOR step, the round constant step only applies to this byte here. So the round constant only applies to the first of the first of the 4 bytes here. With whatever the polynomial x to the I is, so that starts out with I equals 0, but it implements each time we call the key expansion core. And so that in getting bigger every single time is the problem, because once we get beyond x to the 7th, we can't fit that into a byte. So the constant does not appear in binary. It increments as powers of x. So the first few powers look okay, but x to the 8th and x to the 9th have to be reduced mod p before XORing. So this is exactly what we would get for x to the 8. So we talked about that. I'm just putting it in the slide as well. So that's how the expansion core works. That's a function that we call inside the entire expansion key routine. So here's how the expansion key routine works. We have 128 bits, which is 16 bytes. We need 11 different keys, and 16 times 11 is 176. So we have to build the expansion key up to a length of 176 bytes. So while the length is less than that, we're going to go through this sequence here. So we, out of those 4 bytes in each block, okay, we're going to go through these steps here. So we're going to assign temp1 to whatever the last 4 bytes of the expansion key are. If j is equal to 0, in other words, the very first time through this loop, we will go ahead and apply the expansion core to this temp1 step. Then we're going to take the last 16 bytes of the expansion key and the first 4 bytes of temp2. So we're taking 4 bytes, but from 16 bytes away from the end, if that makes any sense. And we are going to XOR these 4 bytes with whatever 4 bytes comes out of the core. That's what's going to happen. And after we've XORed that, we are going to append that to the expansion key. So the expansion key is going to get longer and longer and longer up until the time that we hit 176 bytes or longer. So we're good here. I mean, this is just a routine for doing some manipulations on temp1, and then just as an extra bit of security, having that output being combined with 4 bytes that are, earlier in the string somewhere at sort of a undisclosed location here. So in the 192-bit mode, everything works the same way, except that we just have to change some numbers now. So we now have to have 208 bytes instead of 176 in order to have a different 16-byte key for all 13 rounds this time. While the expansion key has a length that's shorter than that, we're going to go through 6 steps here where we take the last 4 bytes of the expansion key, apply the core to it, and then take the last 24 bytes of the expansion key, and we don't want all 24 bytes, we just want the first 4 of them. So we're, from the end of the key, we go back 24 bytes, and then we take 4 bytes from that chunk. So at the beginning of that chunk, that's what's happening there. So we're reading backwards to get to the starting place, and then we read forwards 4 bytes. And then we take those 4 bytes from temp2 and add them to the outcome from the expansion core. So we XOR those 2 together, and that's the thing that we're going to expand to the expansion key. So that's how the 192-bit version works. So let's talk about what's going to happen in the 256-bit version. Again, this number is going to get even larger. It's still going to be 12 rounds, but it's now 14 rounds. So we're going to have to go to a 15th round. 15 times 16 is, how much is that? 160 plus 80, 240. So we then go up to 240 for the length of the expansion key. All right. So as this number keeps getting larger, the individual steps become a little bit trickier. So one of the things we're going to do is we're going to add this new step at the, assuming the 0th time through the loop. That's the first time in the loop. We go through the key expansion core. But then the fourth time go through the loop, we don't go through the full core, but we still do the SBox step. This step is new, and it gives us a distinction between using these 256-bit keys or using a pair of 128-bit keys. It makes this encryption different from just doing the 128-bit encryption that at 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. In the 128-bit version, we would have an key that goes through here, and then that's the first time, and we go through the whole core for this, and then we're expanding the rest of these. For the 256-bit version, we're going to have twice as much data, but we want at the next group of 16 bits to have something a little different here, but not a full expansion core. So this is a key expansion core step. This is just an SBox step. So that if we were doing 128-bit keys, we would get a key expansion core here and here and here and here and here. By doing 256-bit keys, we get a key expansion core on the left, then an SBox on the left, then a key expansion core on the left, then an SBox on the left. It's a new step, and it just makes the encryption a little bit different in 256 from doing 128 keys. So that's what's going on. Then this step is about the same. We read back 32 bytes, then go forward 4 bytes and take that, and that's our temp 2. We XOR that with temp 1, and that's what we're going to add to the expansion key. And then we keep doing this until we get up to 240 bytes. So key expansion is a little confusing because we have different modes that we have to work with. But once you get them working, they're not too bad. All right. So this is the last day of material for the exam. After the exam, we're going to go back through these individual steps. Add round key, subbytes, shift rows, and we'll talk about implementation details, but I think they're pretty straightforward in most cases. All right. Thanks for coming. Have a fantastic weekend.